So you ready to jump into the next chapter? It covers Bernoulli's equation, which is really an energy equation. Have you heard of Bernoulli before? Bernoulli's equation? Everybody in technical physics, I'm sure you had to use it. Okay, so let me just encourage you to review this, read this section, and maybe go back and look at your physics book as well. It starts out not with energy, but it has to cover mass and conservation of mass and mass balance equation. Then it can get to the heart of the chapter, which is energy, conservation of energy, talking about the forms of energy, and then explicitly Bernoulli's equation, which is very versatile and used in fluid mechanics to solve and predict fluid behavior, solve problems. There's something called a volumetric flow rate. Let's say I have my control volume here, and right in here is a patch of area. I can define the outward directed normal, and so I can write either dA, that's common, or I can write N dA. Okay. If you say dA, you're indicating that that's a vector entity. It has direction and magnitude. The direction is outward directed, and its magnitude is proportional to how much area you're talking about. Here they separate the direction from the magnitude. Okay. If I say I have a velocity v, and let's try and draw a couple cases here. I think I've done this, but if I have the velocity v right here, and this is n, how do I calculate the flow rate going across or through that little opening? V dot n dA. It's a dot of two vectors, the velocity vector at that opening of the fluid that's trying to get through it, times the outward directed normal vector for that surface, for that opening, times the size of that opening. True? Thinking SI units, what are the SI units for this entity that we would calculate? Well, this would be meters per second. This is meters squared, so it'd be meters cubed per second, wouldn't it? Wouldn't that be? And that's volumetric. How many liters or cc or meters cubed, huge entity, cubic meter per second go through that area or cross that boundary? If we played this game, but I'll do it quickly here. If the area is like this, then n is outward directed that way. True? Okay. Let's try and draw a bunch of these that are the same orientation. They have the same size and the same n. And then what we'll do is we'll say the velocity v is this for that case, that for that case, that for that case, this for this case, and this for this case. True? Have we done these? Talk about case A. It's outflow, isn't it? What about case C? No flow. No flow. Even though the velocity is not zero, it's not equal to zero, but it's not crossing the boundary. What about case E? It's negative. It's not outflow, it's negative outflow, which is inflow. Okay. So that's all a good review of the volumetric flow rate. Some textbooks say, oh, we want to introduce a symbol Q, and Q is my volumetric flow rate. I like to avoid the use of Q as a new symbol because we've got so many symbols already. But there is the notion or the idea of the volumetric flow rate. Somebody says, I want you to calculate the mass flow rate. How would you calculate the mass flow rate? Yeah, the symbol is m dot rho v dot n dA. Or just take rho and multiply it by the volumetric flow rate, whatever symbol you want. I like to use V average times A, or just AV as the volumetric flow rate. So this would be the mass flow rate. So if I wanted to calculate the mass flow rate across or through that opening, that's how I would do it. If you wanted to sum them all up, you'd do the surface integral, and we've talked about that before. You could talk about the surface integral over dA, which would be rho v dot n dA. Or you could do it this way. You could do the integral of rho dm. It's the sum of the mass flow rates coming out. But often just leave it like that. How about if I have a nice pipe? The center line of the pipe, the fluid packet, no matter where I'm at, the fluid packet's always heading in the same direction down the pipe, true? And actually, if I take and put a velocity profile, it looks something like this, indicating that the center line, I would think it's going fastest at the center line. So I'll draw the length of that blue vector down the axis to be longest, indicating the greatest speed. And then maybe halfway out toward the wall, it's slower, but it's not zero speed. And then at the wall, because of the no-slip boundary condition, it has to have zero speed. So that would be a velocity profile. So here's a question. Somebody says, I like to have average velocities. So just sort of take this velocity profile and just sort of find the average, so that if I multiplied the area of the pipe times this velocity average times rho, I would get the mass flow rate through the pipe, across each cross section of the pipe, right? It's like this is a cross section of the pipe, cross section of the pipe, the mass flow rate through each of those cross sections of the pipe would be the product of the density times the area times the average velocity. Somebody says, but we just learned how to do that using integral. Rho v dot n dA. Integrate that over the cross-sectional area of the pipe. Does that equation make sense? Okay. What I would need to do, though, in that case is I would need to know V as a function of R. And that lowercase r runs between 0 and cap r. So it's lowercase r going out. N is always down the axis of the pipe. V is always down the axis of the pipe, so that dot product just turns into the rho V dA. That's it.
That's V max.
That's not V max. That V right there is a function of R. I could write it like this. I could say that is V as a function of R dA. Some people do that, but then somebody says, is that V times R, where you're emphasizing R in parentheses, or is that V as a function of R? It's V as a function of R. Yeah? This gives us the equation for the average velocity. The average velocity is, especially if I have incompressible, most of the time it's incompressible, you just cancel it off, is equal to the integral of V dA 1 over A. Or just put it like this, over A. Makes sense? So we could talk about the average velocity in a lot of cases. Here's a problem. Let's go ahead and go through this problem. Air enters a control volume at a pressure P1 of 600 kilopascal, a temperature of 500 Kelvin, and a velocity of 30 meters per second through that inlet area of 28 centimeters squared. So it's an inlet area of 28 centimeters squared. It exits at pressure 300 kilopascal. A temperature it exits at, we'll call that state 2 for exiting, 475 Kelvin, and a velocity 2 of 280 meters per second. Air behaves as an ideal gas. When you see that ideal gas, it's P equal to rho RT. What is this R right there? R bar divided by the molar mass? Right. So if I want to calculate rho at state 1, often I'll write it like this. I'll say the pressure at 1, using this ideal gas equation, the molar mass of the fluid, the ideal gas fluid, in this case it's air, divided by R bar, T at 1. So we know all of those values, don't we, for this problem? And so we can just go ahead and calculate it. I'm going to need it to answer the question, which I haven't fully read the problem yet, but this just comes in at 4.1814 kilograms per cubic meter. There's some density. All right. Let's continue to read this. Assume it's steady state operation. What happens if it's steady state? Well, the mass flow in at 1 is equal to the mass flow out at 2. True? That's what we use. It says calculate the mass flow rate of the air. So what is the m dot? It's going to be rho in, area in, velocity in, rho AV. And the only other thing to be cautious of is I'd like this in meters squared. So 28 centimeters squared, you can kind of put your finger and say, oh, that's a centimeter, okay. How much is that by meters squared? And it's 0.0028. True? Make sure we don't miss that simple conversion. And when you put in the numbers, you'll calculate that the mass flow rate is 0.351 kilograms of air per second passing in and then out of the control volume. How about for part B? What's the exit flow area? We want to find this A2. Well, the mass flow rate is equal to rho 2 A2 V2. So the exit area is the mass flow rate divided by rho 2 V2. You do the same calculations for the density at state 2. P2, molar mass of air, R bar T2. And that density is different. It's 2.2007 kilograms per meter cubed. The velocity is given, and so you calculate the exit area to be 5.7 centimeters squared. Make sense? That was almost too easy of a problem, wasn't it? Yeah, I hope they're all like that. Well, now that we have mass and volumetric flow rate and mass flow rate, mass balance equation, let's move to the energy. Well, we're going to talk about the total energy being conserved. But the total energy is made up of internal and mechanical forms of energy. So for our open system, this equation, which we derived using the Reynolds transport theorem, you can identify a control volume, and you have rates of heat transfer into the control volume, shaft work into the control volume. If it's steady state, we're going to neglect that, how the energy accumulates or goes up or down with time in that control volume. But here is the flow across the boundary of the control volume. E is the internal energy plus the kinetic energy plus the potential energy. The PV comes from that boundary work that gets lumped in. And so when we add the PV there, we get that it's H plus the kinetic energy plus the potential energy, where you recall that the enthalpy is U plus PV. It's nice to go back to firm ground, like, oh yeah, I passed thermo, I understand that energy equation, I understand enthalpy, right? So that's good. So, but I'm interested in I can take this total energy equation and say, all I want to do is talk about mechanical energy of the flowing fluid. We often do this. So we're not interested in heat transfer. Okay, so you take that Q dot out. We're interested in steady state, yeah, so we drop that term. We still have shaft work, but we're really not interested in changes in the temperature of our fluid, which is often incompressible. Hence, we're not interested in changes in U. U would be constant. We leave that out. Okay? U's the same everywhere. So the equation boils down to, the energy balance equation boils down to only these components. If you're interested in a conservation of mechanical energy equation. Now, how do I write this with one inlet and one outlet? This would be like the mass flow rate going exiting, and then you have the PV plus 1/2 V squared plus GZ exiting minus PV plus 1/2 V squared plus GZ coming in times the mass flow rate coming in. True? But we said that they were the same, it's steady state, so these M dots are the same. That's the same mass flow rates. So you can even combine it. So it's PV exit minus PV inlet plus, let me write it as KE exit minus KE inlet plus PE exit minus PE inlet equal to W dot shaft in. So if I have some fluid flow going through a system, control volume, comes in, mass flow rate, goes out, mass flow rate, state 1 on the inlet, state 2 on the exit, then it would be like PV2 minus PV1 plus, then you have the KE2 minus KE1 plus PE2 minus PE1, true? All times mass flow rate equal to W dot shaft. You can think about this representing a pump. And a pump, yeah, you have to supply shaft work into the pump. What's the purpose of the pump? The purpose of the pump typically is not to change the kinetic energy of the fluid or to change the potential energy of the fluid, but it's to change, and not even to change the specific volume of a liquid. Usually pumps apply to liquids, but it's to change the pressure. And so you can go back and revisit problems that you've solved in thermo. Let's do this. Let's take a fluid chunk right here and follow it as it flows through my flow field. That's a streamline surrounded by other flow chunks that flow. And now what's that? That's a stream tube. Let the stream tube be my control volume and apply the conservation of mechanical energy to the control volume, where we have a number of assumptions. But we'd have W dot shaft coming in equal to the mass flow rate times the change in PV plus the change in KE plus the change in PE. True? One more thing. For Bernoulli's equation, 0. So I'm not adding mechanical energy, no flow in from a shaft work or out. In that case, it's this sum that must be equal to 0. True? M dot's not going to be 0, so the product of M dots on something must be equal to 0. And if that's true, what you have is you have the PV coming in plus the kinetic energy coming in plus the potential energy coming in is equal to the PV going out. Let's say this is in at state 1 and out at state 2, plus kinetic energy out at state 2 plus the potential energy out at state 2 is all equal. This is potential energy. A lot of times they'll write like this: pressure times the specific volume plus 1/2 V squared plus GZ is equal to a constant.
Yeah, the GZ was 0 is what I'm wondering, because there's no change in 1 to 2 altitude.
Well, I may have not drawn it like that, but yes, in general, the exit could be at different elevations, and often is, when you apply Bernoulli's equation. But this is one form of Bernoulli's equation. Does it look familiar to you? Can you follow the derivation? It's really a subset of the energy conservation statement. It's a mechanical energy. So let's go back and review some of the assumptions that were here. Well, what about steady? Isn't it steady state? Do we have anything about the fluid being incompressible? You can modify it for transient. We're not doing that. Let's leave it at the generic Bernoulli's equation. And it's incompressible. It's also, do we have any friction in it? Do we have any mechanical dissipation mechanical energy? In real systems, we have head loss, we have that viscous effects, but we would say it's inviscid. What does that mean? Frictionless. Negligible viscosity, negligible losses. And it's along a streamline. So those are a number of the assumptions that go along with Bernoulli's equation. How many people recall solving problems using Bernoulli's? Okay. So did I miss any? Oh, there's no heat transfer. There's no Q. Well, Q dot equal to W dot equal to 0. No heat transfer and no work transfer. We can modify Bernoulli's to account for some power in and power out later with the mechanical work. How many people recall seeing a different form of Bernoulli's? The one we just derived is the pressure times the specific volume plus 1/2 V squared plus GZ is equal to a constant. Who recalls a different version of Bernoulli's? Do you remember? How did you learn Bernoulli's equation? Did you learn it as P plus 1/2 rho V squared plus rho GZ is equal to a constant? Anybody? Well, you say, well, these look like they're the same equation. Well, sure, they are. What did we do here? You just multiplied by density. True? There's one other form. There's 3 forms of Bernoulli's equation. They're all just related to each other. Very simple algebra. But another form is P divided by rho G plus V squared over 2G plus Z is equal to a constant. How did we go from this form to that form? You multiplied by 1 over G, or divided every term by G, true? Okay. These equations all have some sort of SI units. What are the SI units for the middle equation? Can you tell right away? What are the SI units? Meters squared per second squared. Will that work? You can. We know that the equation is correct, and hence it has the dimensional homogeneity. It must be dimensionally homogeneous. That means this term has to have exactly the same units as this term plus that term, and they add up. Otherwise, it's not going to work, right? And so what you do is you just sign one of the terms is easiest to see the units from. And most people would say, you know what, I can see the units in the most simplest form from that middle term of that middle equation. And they're meters squared per second squared. How about this first equation, SI unit?
Kilograms over meters times second squared. Or pascals if you want.
How about this? If you just said from dimensional homogeneity, they all three groups have to have the same units. I look at P. P is pressure. Pressure is Pascal or Newton per meter squared, Pascal or Newton per meter squared, something like that. Both are acceptable. How about the last one? I look at all three of those.
Meters.
It's meters. SI unit of meter. By focusing on the easiest one to see the units of. Elevation, Z, which is in meters. Now, each one of these, Bernoulli's equation, is a statement of the conservation of what? Mechanical energy. It doesn't appear to be so obvious that each of these three forms are some energy statement equation, like energy conservation equation. But probably this one is the easiest one to see because you recall that 1,000 meters squared per second squared is a kilojoule per kilogram. And a kilojoule is energy, and a kilogram is mass. So we can interpret that middle equation as, oh, it's energy per unit mass. The mechanical forms of energy per unit mass are being conserved along that streamline, steady flow, inviscid, incompressible, blah, 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 right? Well, look at this one above. How do I make that look like an energy per something? Well, if I multiply a Newton by a meter, what do I get? A joule. So I had to put a meter over meter. And then what is a meter cubed? So this would be energy per unit volume. A little chunk of mass going along the streamline, you can think about its little bit of mass. You can also think about its little bit of volume going along the streamline. And so that energy per little chunk of volume is conserved. The mechanical energy per chunk of mass is conserved. The last form is the most difficult for students and everybody else to see. How do I make this turn into an energy per unit something? You want a joule over something. I know I had a kilojoule in the first and just a joule in the next, but if I just multiplied by a Newton divided by a Newton, what does a Newton times a meter? That's a joule per Newton. Okay, I interpret joules as energy. So this is an energy per what? Force. Okay, I talk about my little chunk of fluid. It has mass m and it's flowing along a streamline. I talk about the volume that that little chunk of fluid has as it flows along the streamline. So I can identify the mass of a little chunk of fluid. I can identify the volume of a little chunk of fluid. Do I have the concept of a force per chunk of fluid? Maybe that's not the best word. I know that Newton is a measure of force or units for force, but let's find another word that makes more sense than force. What is it?
Per unit weight.
Per weight. If I gave you a little chunk of fluid, okay, and I said, could you give me its mass? You would say, sure, I can. I mean, yeah. How about also its volume? Yeah, I could measure it. And could you give me its weight? Sure, I can give you its weight. If you give me its force, it works better if I say its weight. So it's the energy per unit weight. Weight of what? Little chunk of fluid that's going along a streamline. Just like energy per unit mass. Mass of what? It's a chunk of fluid going along a streamline. Energy per unit volume. Volume of what? The fluid's volume as it sweeps along a streamline. And so all of these statements are out there. They're widely used in engineering. Sometimes you'll see this form used, that form used. And it's hopefully getting this roadmap down in your mind makes it a lot easier to solve problems. Ready to solve a problem? Water flows in a pipe where at point 1, here's point 1. The pressure at 1 is 160 kilopascal. The velocity at 1 is 1.5 meters per second, and the elevation Z1 is 16 meters. At point 2, some other point, maybe I'll just show it over here. Point 2, the pressure is 175 kilopascal. Did the pressure go up or down? It went up a little bit. Okay. The velocity at 2 is 2.3 meters per second. Did it go up or down? It went up a little bit. And the elevation's not known, but they say, what is the maximum possible elevation at point 2? So I'm asked to calculate Z2 max. That's what I'm asked to calculate. Well, is it going to be the maximum if I have inviscid flow, negligible frictional losses associated with flow in a pipe? Sure. So basically you apply Bernoulli going from 1 to 2. Everything in the problem says it's steady. When it says water, I know we have to sometimes make an assumption about water, but it's incompressible. It's incompressible. And so what we have is we have to say that P1 plus, applying Bernoulli's equation, P1 plus, what form do you want to use? Do you want to work in pressure, energy per unit volume? You want to work in energy per unit mass, or do you want to work in elevation? We could do all three. I mean, they're all just either multiply by rho, divide by g, or you're there. I mean,
we're looking at elevation that's already set up.
Yeah, let's just do it in head then. I forgot to emphasize, this version is called head. This is just the pressure form. This one is just energy. Somebody said, we'll just use Bernoulli's, and it's just because it's energy per unit mass. But head is the one a lot of civil engineers use. Let's use that version of it, okay? So we would say that P1 divided by rho g plus the velocity 1 squared divided by 2g plus z1 is equal to, keep it in the same form, P2 divided by rho g plus v2 squared divided by 2g plus z2. Did I do that correctly? And so we find that z2 is equal to z1 plus p1 minus p2 divided by rho g plus v1 squared minus v2 squared divided by 2g. You have to be careful on units, so this would be 16 meters plus. I have 160 minus 175. It's kilopascal, so kilonewton per meter squared. And then rho g, oh man, I've seen that before. Sometimes they call that gamma. It's a weight density. Rho g, weight density, right? I can't remember. What is that for water? 9.81. I try to show that where gamma for water is rho g of water. It's 1,000. This is the last time, I promise you. But when I graded the exams in the fluids, I noticed so many people were spending a lot of time. If you just know, hey, I'm dealing with water, it's rho times g. Why do I want to put g as 9.81 meter per second squared? It just, just do it once so that you know that it's a kilogram per meter cubed times 9.81 meter per second squared, and then you recall that a Newton is a kilogram meter per second squared, and you get the second squared go, the kilograms go, this meter goes with that one, and I'm left with a 1,000. Let's replace that 1,000 by a kilo. So 1,000 goes, and so I'm left with 9.81 kilonewton per cubic meter. So that makes sense right there, rho g. True? Okay. And then we're going to finish this out. We have V1, which is 1.5 squared minus V2, 2.3 squared. Both of those have meters squared per second squared divided by 2 times 9.81 meters per second squared. Did I do that correct? Who has a calculator can run that for me, please? Good, 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 good. Thank you very much. Anybody else confirm? Be careful on units, right? I mean, just that's all of engineering, isn't it? You have to be careful on units. So we know then that elevation is that. This is the maximum possible elevation. If you'd have some frictional losses, guess what? The actual elevation is going to be lower because some of that mechanical forms of energy went somewhere. Where did it go? Frictional into internal via friction. Okay. Consider incompressible fluid flow in a horizontal pipe. The density of the fluid is given. So rho is 700 kilograms per cubic meter. The pressure and the velocity of the fluid is measured to be, so the pressure is 150 kilopascal and the velocity is 1.25 meters per second at a specified point. Let's call it point 1. If the pressure is 140 kilopascal at another point, determine the maximum possible velocity of the fluid at that point in meters per second. Okay, so what is V2 max? There's a key word right here. Horizontal, delta Z is 0. So Z1 is equal to Z2, true? So let me just say Z1 is equal to Z2. Well, we would apply Bernoulli's, assuming steady flow. There's nothing to indicate transient. It's incompressible, long streamline, blah, blah, blah. In this, it's so what form of Bernoulli's makes sense maybe for this one? Yeah, we can do that one. So it would be that the pressure at 1 divided by the, well, either multiply by V or divide by rho, P, right? Plus 1/2 V1 squared plus GZ1 equal to P2 over rho plus 1/2 V2 squared plus GZ2. Is that correct? Did I write it correctly? Got one thumbs up? Anybody else say it's correct? 2, 3, 4, 5? Good. These are the same. And so we get that V2 maximum is equal to the pressure at 1 minus the pressure at 2 divided by the density multiplied by 2. I left it off. Thank you very much. So we have plus V1 squared square root. Now it's good. Yes or no? Is that okay now? Thank you for the correction. Let's just do the difference in the pressure. So it's 150 minus 140, that's 10. And I'm going to put kilopascal, how about kilonewton per meter squared? 1,000, no I don't, I have only 700. 700 kilograms per cubic meter, true? And I'm going to leave some room right here. Let's do the unit conversion right away. Newton is a kilogram meter per second squared. So that Newton goes, but don't watch out for that kilo. And then we have the kilograms go, and then we're going to be left with, get rid of that one, get rid of that one, get rid of that one, turn it to 2 meters squared per second squared. That's what we're going to be left with this kilo. So let me do this. Let me put the kilo here and 1,000 there, because a lot of people will forget that kilo, that 1,000, factor of 1,000. Okay, let's finish out with the plus. The 1.25 meters per second, parentheses squared, square root the whole thing. So there you go, 5.49 meters per second. Torricelli's equation. You have Bernoulli's equation. You also have another equation. Sometimes it's called Torricelli's equation. Let's start this problem. I have a tank that's going to hold a fluid, but at the near the bottom of the tank I have an outlet. And so the tank is filled with some fluid. And the valve, maybe that used to be there, or the stopper has been removed, or the seal's been broken, something, and now I can have fluid just gushing out right down here, out that hole. Okay? And we're probably told something like, oh, the diameter of that hole is small, and you could do some calculations with it. But somebody says, I think you can calculate the velocity of the fluid coming out of that hole. Can you please calculate the velocity of the fluid exiting that hole? Yeah, okay. What I'll do is I'll start right here, and I'll go with a line. That line represents a streamline. If I wait long enough, the fluid packet that started here would slowly go, and finally go out. And so along that line, I have state 1 to start it and state 2 to stop at the end. All right. And I could assume things like conservation mechanical energy along that streamline, inviscid flow, incompressible, steady flow, blah, blah, blah. I know that the fluid level will be dropping, but it's like a sequence of quasi-equilibrium states. It's steady state with the flow. Okay. So if I did that, I could apply Bernoulli's along that streamline from 1 to 2. Let's think about it just up here. P1 versus P2. Which one's greater? P1 or P2? It's right at the exit.
Is there an increase in velocity because of the smaller diameter?
Okay, that's easier, isn't it? Let's do V1 versus V2. Which one's greater?
V2 should be greater.
The V2 is a whole lot greater. Okay. No, yeah, come on now. Go slow here. Where is 2? Is 2 here, halfway down in the fluid layer? No, it's not there. If it had been there, which one would be greater? The pressure here would be greater than the pressure at 1, true? Let's say I move to point, and they call this 3. How about if I go to point 4? Is the fluid pressure at 4 greater than the pressure at 1? Yes. Yeah. But then something special happens, because where did I draw to? Outside. Okay. So picture the tank coming like this, and the fluid chunks are just going like this. Right there. What's the pressure right here in the fluid after, a millimeter after it exits that hole? It could be atmospheric. And those water lines, the streamlines of those water are shooting parallel to each other. They're not curved. And later we'll talk about Euler's equation and how to calculate fluid pressure changes in a bend. But they're straight lines, infinite radius of curvature. The pressure doesn't change. from some location going from the edge to the middle of that stream of fluid shooting out. Hence, the pressure at the edge, atmospheric. Pressure in the middle is atmospheric. It's atmospheric pressure. So, what about P2 compared to P1? This is true. V.
No, it's going to be the same.
It's the same. Pressure is the same. Velocity is a lot higher. What about the elevation? A lot less. I mean, that's what's making it flow. Z1 is high. Z1 is high. So we write Bernoulli's equation. Doesn't really matter what form you want to write. Which form do you want to write? Let's practice. Which pressure or energy per unit mass or head? You want to do the pressure form? So you would say the pressure at 1 plus 1/2 rho V1 squared plus rho G Z1 is equal to the pressure at 2 plus 1/2 rho V2 squared plus rho G Z2. I know a lot of times once we start solving Bernoulli's equations, we just always start with our favorite form. But there really are three, and you can start with any of the three. All right. So we cancel these two because they're the same pressure. We cancel one of the velocities, not V2, that's the exit. That's what we're looking to calculate. But V1 squared is really small.
Does that have to do with the area being so
That's
large?
exactly right. The area of this tank, you draw it large, and that area, the diameter of the tank is much greater than the diameter of the hole. You want to put a hole diameter right there. And then we go ahead and cancel the rows, and we now solve for the exit speed at 2, which is 2, that's what I did with this 1/2, I flipped it up, times G times Z1 minus Z2, take the square root. Does that equation look good? That's Torricelli's equation. The exit speed out of a tank is equal to the square root of 2gh, the depth from the water level to the tank, assuming that the air pressure above the water level and the pressure at the exit are the same pressure. Now, if I take and put a lid on this, and then I pressurize the air above it, forget it. Go back to don't apply Torricelli where you forgot that there's a difference in the pressure between 1 and 2. But if I leave this off, it's air above it, the same pressure. You get Torricelli's equation. What is the Torricelli's equation? Square root 2gh, right? H is that height difference. So let's go ahead and stick in some numbers. Oh, I don't have any numbers. I'd have to substitute some numbers. A large cylindrical tank stands 25 meters tall. Let's go ahead and draw this out. There is the 25 meters tall, and has a diameter of 6 meters. The tank is filled to 10 meters with water. So this is 10 meters. Air above the water is pressurized to 300 kilopascal. This pressure of the air is 300 kPa above. A valve is located at the bottom of the tank. The valve has a diameter of 2 centimeters. Diameter of the hole or the valve is 2 centimeters. What is the minimum time required to fill a 5-liter bottle from the tank? So I have a little tank like here, and it starts at 0, but then it slowly fills up until you fill it up to 5 liters, right? What is the minimum time required? So maybe we're going to look for TF or just T. I hate to just put T because T is time, so probably TF is the time to fill it. I have a subscript on that T. And I'm looking for how many seconds or milliseconds or minutes or hours, whatever unit of time I get for that time. Okay. All right, so I have to use conservation of mass principle because this is water. Water is incompressible. Volume is also conserved for water. True? So if I knew the volumetric flow rate, what symbol do I like for volumetric flow rate? AV. AV. You could use Q, and maybe the book I'll look, maybe that uses some symbol for volumetric flow rate. But if I am able to calculate the volumetric flow rate, I multiply that times the time to fill the tank. That will give me the volume of the tank or bottle. Maybe I should put this as bottle B, volume of B. So 5 liters, the volume of the bottle is 5 liters. Sometimes it's grappling with what symbol do I introduce and subscripts do I introduce for everything, right? Does this equation make sense, yes or no? Thumbs up if you like it. You're good? Okay. Now, so to calculate the time to fill, I know the volume of the bottle. I get the area of the hole, or the, what do I want to call this? Let's call this diameter of the hole, and then the area of the hole. And then I have the velocity of fluid exiting the hole. I'm going to call that state 2. True? And we'll apply Bernoulli's from here to there. Can I apply Bernoulli's out? No, it's an air. You got to stay with a chunk of fluid. The chunk of fluid was water. It can start at the top, and you're letting it drain out. True? So what is the, I forgot, no, that's all of it. What is the area of the hole? Yeah. Right? Okay. What is the velocity at the exit of the hole? V2. What's that speed? You know what? I didn't ask any clicker question at all today. So I'm going to ask one right now. Does V2 is, now let me just say, this is a statement. V2 is a function or depends on the diameter of the hole. The exit speed from the hole, as calculated, we're going to calculate using Bernoulli, depends on the diameter of the hole. A, true, or B, false. Do I need to repeat my question? I'm interested in now calculating V2. Does V2 depend on the diameter of the hole, size? Yes? You say, that's true. Answer A. No, that's false. Answer B. All right. Hopefully 30 seconds was long enough. And we're all over the map. It does not depend on the diameter of the hole. True? So let's go ahead now, just show that. What do we have? We have the pressure at 1. There's negligible velocity at 1 because it's a large diameter tank. Plus rho g. I'm just going to call this the height of the water level. It's 10 meters above the hole. H is 10 meters. Equal to the pressure at the exit, which is atmospheric pressure, P2, atmospheric pressure. Then I have plus 1/2 rho of the water, V2 exit. So let me draw it out like this. V2 is equal to P1 minus P2. What is that pressure? That's my difference in pressure. Yeah, the pressure at 2 is 100 kPa. And so the difference in pressure between the air and the tank, I assumed that 300 kilopascal was not gauge but absolute pressure. Then I have to subtract off the roughly 100 kilopascal atmospheric pressure to get the delta P that's required, this delta P. Okay, let's continue on. I'm going to have plus rho GH of the water. Then I have divided by rho multiply, oh boy, I messed this up a little bit. Put it like this. 2. It then take the square root, and then that's V2. I pause. I ask you to look that over. Do I have any errors, or is that okay? Look okay to you? Couple good, thank you. Look okay? All right, let's substitute numbers in. Oh, I know that most of you have gotten over this, but please, 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 try to work in symbols as long as possible. That's a good strategy for about 90% of engineering problems. This one, I think, is a good strategy. Substitute numbers with units, cancel units. When I teach statics or any other lower level class, that's my main theme. Help students develop good problem solving skills. So let's do this one. 2 times, what did you say, 200? Yeah, it's 200. And then kilonewtons per meter squared plus 9.81 kilonewtons per meter cubed times 10 meters divided by 1,000 kilograms per meter cubed. That looks right. Yeah. And so let me do this. I'm going to put a kilo and 1,000. You can do it a number of different ways. Okay. This I'm going to yeah, I know I'm going to end up making it look messy, but that kilo will get rid of this kilo. Okay. And a Newton is a kilogram meter per second squared. So I'm going to get rid of this. Just a minute. I'm going to get rid of those. I should have put the parenthesis there, right? Okay. And now I'm going to have yeah, all of these meters will work.
Sure you didn't get your meters in second squared for your Newton substitute reciprocated there?
Yes, I did. Meter per second squared. Thank you. So then, yeah, then I take the square root and I'm left with meters per second. There you go. How many got 24.4? 1, 2, 3. Anybody else? Another number? You look good? 24 point? All right. So now, to calculate this final time, the time final, let me write it in here. The time final is 24.417. This is a case where it's better to go ahead and calculate the, that's not the right one, the velocity coming out. Okay, the volume was 5 liters. How many meters cubed is 5 liters? Is that right? 0.005 meter cubed? Yeah. Yep. And then the area, pi, 0.02 meter squared over 4 times the velocity, 24.417 meters per second. Yeah, this right here is Bernoulli's. And I right away threw out some of those terms that I knew were 0. Okay? Let's say that somebody says, oh, no. Look, this is gauge. I'm reading 300 kilopascal gauge pressure. What would happen to the time required to fill the 5-liter tank? Go up or down or stay the same?
It would go up.
Okay, clicker question. So we have somebody says that it's 300 kilopascal gauge in the tank. Not absolute pressure, gauge pressure. Does the time to fill, does it go up? So it's not 0.65 seconds, but maybe 0.8 seconds or something like that. Is it longer? That's answer A. Stay the same, answer B, or go down, answer C. And we'll start it right now. Somebody says it's not 300 kilopascal absolute, it's 300 kilopascal gauge. You know, if somebody said, oh, that's 300 kilopascal gauge, wouldn't that be the same as saying that's now 400 kilopascal absolute? Higher pressure, pushing it out faster, it would fill the tank quicker. So the time to fill it would go down. The time to fill it would go down. It wouldn't take 0.6, maybe it'd take 0.5 seconds, right?
I changed my answer to B, meaning C.
Oh, did you? And you meant C?
Yeah, well, obviously, I told you that they're inversely the velocity of time.
Yeah.
Stupid.
I'm gonna go ahead and stop here. If anybody has questions for me, I'll be up in my office. We can go over exams, etc. Okay? Thank you very much.